Okay, hi everyone. So we've covered gravitational fields, we've covered electric fields. We're going to be moving on to the last type of field that we're going to be looking at, magnetic fields. And this is going to tie in quite a bit with the stuff we've done on electric fields. You'll be seeing a bit of overlap between electric forces and magnetic forces over the next couple lessons. So when we're talking about magnetic fields, they're produced by magnetic materials and they exert forces on other magnetic materials, or materials that can become magnetic, like iron nails, that sort of thing. So we've got that kind of correspondence with the gravitational and electric fields, where the things that produce the fields are the same things that are affected by the fields. Holy Christ, that was a big swing. I'm going to keep running. This swivel's probably not worth the effort of using it, but whatever. So gravitational fields, we're going to introduce some new terminology. We're going to call some things monopoles, and some other things are going to be, where's the word written down, dipoles. So if you think back to gravitational fields, it's going to follow me, right? You had like the Earth, it was one thing, it produced field lines that pointed in towards it, it was one on its own. If you think about electric fields, you could have a single positive charge or you could have a single negative charge. That was a monopole. It's one kind of thing that produces a field. Or we could have what we call a dipole setup, when there were two charges next to each other producing a combined field. Like when we had a positive charge and a positive charge, we had a combined field that was due to the effects of both those charges, or we had a positive and a negative, or a negative and a negative next to each other. The two fields combined together produced a dipole setup, where we've got two poles, di just meaning two, so that's just what that means. Gravitational fields were always monopoles. Electric fields could be monopoles. You could have one positive or one negative, or they could be dipoles. Magnetic fields we're going to look at today are always going to be dipoles. You're always going to have a north pole and a south pole for your magnetic field. You can't just have a north pole or a south pole on its own. So we call a magnetic field a dipole because they've got two poles. Easy. If you cut a magnet in half, we're just visualizing magnetic fields as being made by simple bar magnets with a north and a south. If you cut it in half, you don't get a north end and a south end. What you get are two smaller magnets, each with their own north and south poles. So we can say that there are no magnetic monopoles. If you take a magnet with the north and a south pole and you separate it in half, you just get two smaller versions of your larger magnet, each with their own north and south poles. It's important to keep that in mind, that magnetic fields always dipoles, never monopoles. Now, when I show the magnetic field of a bar magnet, it's going to look pretty similar to that setup that we had with a positive and a negative charge. You remember we had a positive charge with field lines coming out of it, and we had a negative charge with field lines going into it. So this setup is pretty much the same as when we had those positive and negative charges, the field lines going between them, field lines going from north, pointing away from north, always towards south. That's the convention that we use when we show field lines. The lines are always pointing away from north poles towards south poles. When we did electric fields, they always went away from positives and towards negatives. So there is kind of a correspondence and analogy to the electric fields from this. So bar magnets are just our most simple version of a magnetic field. And as part of doing this course, you often need to know what the field lines around different magnetic setups will be. And this is the most basic one that we get. It's also important to know that when we're talking about the Earth, its core is made out of iron. And so as a result of that structure, the Earth produces its own magnetic field. Now, the thing to keep in mind with the Earth's magnetic field is that it's going to change orientation over long periods of time. The north and south magnetic poles shift. I think it takes tens of thousands of years for that to happen, and we're a bit overdue for that to happen to us, so it might happen, but it takes a long time once it's initiated for it to, it's not just a sudden, the magnetic poles have switched overnight. It's a long process. At the moment, the Earth's magnetic field is oriented so that the north pole of the Earth's magnetic field happens to be at the south magnetic pole, or the south geological pole of the Earth. So this is just an inconvenient and kind of unpleasant part of looking at this stuff. That you think North Pole, the North Pole geographically is up here, the North Pole magnetically we say that this is the North magnetic pole and that's the South magnetic pole. If we actually look at the physics behind the Earth's magnetic fields, then the field lines are pointing away from down here up towards here. They're pointing around in this direction, which implies that this has to be the north pole of the Earth's magnetic field, and up here has to be the south pole. So just keep that in mind, that when we talk about the Earth's magnetic field lines, the field lines are pointing from the south towards the north, in opposition to how on the last slide I showed they work. They point away from north towards south for a magnet. And so we say that the magnetic field of the Earth basically has its north pole down in the south. We still call this the south magnetic pole, even though it corresponds to a north pole on a magnet. It's just some really unpleasant sort of terminology that you come across when you some inconsistency in the way we use the language. This is how the Earth's magnetic field works, and so just keep in mind that when we're talking about the Earth's south magnetic pole down here, it's actually more like a north pole. The field lines are pointing out of it rather than into it, and you'll come across that in a few questions like we're doing today. Now, up here I've just got a north and a south pole. We could set this up with like a bar, or what do you call a horseshoe magnet, connecting these up. So even though it looks like, well, there's one north pole and one south pole, and didn't you just say that there are no magnetic monopoles, and how's this make sense then? You could have some kind of system connecting them, or you could have a south pole there and a north pole there. Same thing with the south and the south there. I've just picked this picture out because it simplifies things down a bit. So this is when we have two separate magnets, or the field lines around one set of magnets. Yeah, this picture's not ideal now that I'm thinking about it, but whatever. And it basically shows the field lines in between those two poles. If I go back a couple of slides, this is what the field lines looked like around a single magnet, a single bar magnet. Here we've got separated poles, and this is the configuration between them. Remember, this is basically like a positive charge, and this is a negative charge in terms of the field lines. Field lines coming out of the north towards the south. If you looked back at the electric field line stuff that we did a couple lessons ago, this would look essentially exactly the same as the setup where we had a positive and a negative, and this is the same as when we had two positives. The field lines kind of asymptoting towards a line in the middle, pointing away from the two north poles. So these configurations, where you've got unlike poles, you might remember from your Year 7 science that when you've got two unlike poles, they're going to have an attractive force between them, so they're going to be pulling in. When you've got two like poles, there's going to be a repulsive force. These are going to push away, and so their field lines are going to basically be not meeting up. They're not going to want to join together. They're going to, if you imagine pushing these together, the field lines are going to squish and push away from each other. Just giving a thumbs up to Wombat there. So just keeping that in mind, it's something you're expected to almost sort of memorize. If you've got a magnet or a set of poles, this is what the setup between them would happen to look like. Now, that's a bit of background stuff. Really, that's just stuff that it gets taught as part of Year 7 science, so it's not that new to you, I hope. What's probably going to be new to you is that when we're talking about charges, a moving charge produces a magnetic field around it, and we're going to be looking at, in particular, the magnetic field that is produced by a wire that is carrying some kind of current. So I've got some pictures here. We've got a wire carrying a current. The direction of the current is shown by the arrow up here. And so what we're saying is that the charges moving along a wire, the current that's moving along it, is going to produce a magnetic field around the wire. So just keep that in mind, that moving electric charges are the cause of magnetic fields when we're dealing with this stuff. And what was I going to say? I'm having a mind blank. This is going to kind of get into some of that stuff you would have done as part of Year 11 electricity, where you look at how when we've got a current, we're going to say that a current is the direction of movement of positive charges, even though in reality current is the opposite direction motion of negative charges, of electrons. So when we talk about current, we are thinking that these are positive charges moving along there. That's not actually true, but it's what we think of current as being. And it's going to kind of matter when you have to worry about the direction of current and the direction of the magnetic fields, but just keep that in mind. So the magnetic field lines are going to take the form of concentric circles around the wire. We've got these circles around this point. The magnetic field is going to look like this. As you head away from the wire, this is where the magnetic field would be pointing. You can just use these field lines to figure out the direction of the magnetic field at different points. And this is what our field line pattern is going to look like for any wire. We've got a set of circles. The only question you really need to ask yourself once you know that is, are the circles pointing around this direction, which I guess from my perspective is going to be anti-clockwise, or are the field lines pointing in the reverse direction clockwise? You've basically got to determine which direction the lines are going to point in. And to figure that out, we're going to use something called the right-hand grip rule. We've got two right-hand rules we're going to learn about. The grip rule is, I guess, the less fun one, but you still use it anyway. So I've got a wire. It's carrying a current. Let's say that the current is flowing from the bottom to the top. Now, I'm going to align my thumb, as you can see in the picture here, so that my thumb is pointing up. Now, this is called the right-hand grip rule. The idea being that I'm going to grip my wire, maybe move it a bit closer so you can see, grip my wire so that my thumb is pointing in the same direction as the current. My thumb's pointing up. And the point is that my fingers are going to wrap around from my knuckles to my fingertips in the direction of the magnetic field lines. So if I'm gripping it like this, the direction around from my knuckles to my fingertips, so from there around to there, that's going to be the direction of the circles. So I draw a set of concentric circles. If I was drawing the field lines for this, I'd draw a set of circles around the wire, and the direction of the wire field lines, I guess this is a bit of a perspective thing. This is anti-clockwise from me, from where I'm standing, from above. Don't know if it'll look different for you, but I've basically figured out what direction my field lines are pointing in, because remember, thumb in the direction of the current. If I've said the current's up, thumb is up. If I was to change it and say that the current was down, I just grip it like that, and I can see now that my field lines are now pointing in a clockwise direction according to me. They've switched direction because my current has switched direction. So that's the right-hand grip rule. You just use it in the context of there's a current carrying wire. It is producing a magnetic field. What is the direction of the magnetic field around the wire? And the language that we use around this with a current carrying wire, that's important language. Often on the exam, if you just say a wire produces a magnetic field, well, no, it doesn't. Wires aren't necessarily magnetic. But if there's a current flowing through it, then the current carrying wire, that's what produces the magnetic field, and that sort of terminology is something that does matter as part of this course. Now, the other thing to do with this, there's going to be actually quite a bit of stuff, is that current carrying wires, stuffed up, well, I just said not to stuff up. Current carrying wires produce magnetic fields. Those magnetic fields are going to interact with the magnetic fields of other wires. So I'm putting the PowerPoints up on Compass, so if you can't see this clearly, then you can just check on there. But here we've got two current carrying wires. They're both carrying wires upwards. You can see in the middle, their magnetic fields are pointing in opposite directions. This one's going that way, and this one's going that way. Because these two wires in the middle have opposite oriented magnetic fields, these two are going to attract each other. They're going to pull in towards, because their magnetic fields in the middle are opposites. You could say one's a north pole and one's a south pole. The exact question of where north and south are on these is a bit vague. But the point is that because their fields are opposite, those two are going to have an attractive force between them. It shows in this diagram, currents in the same direction, forces attract. Currents in the opposite direction, one up and one down, these are going to produce a repulsive force between them. So when we talk about magnetic fields and magnetic field strength, we're going to kind of do things a bit differently to the way that we did when we were doing gravitational and magnetic fields, because magnetic fields are more involved in terms of the calculations of forces, and you might be like, well, how strong is the magnetic field strength produced by this wire? We're not going to do calculations of magnetic field strength really in terms of how much current and how far away from the wire you are. So just keep that in mind, that we're not going to do exactly the same stuff for magnetic fields that we did for gravitational and electric fields. It's not going to work quite the same way, just because magnetic fields have more to them than the others, and we don't go into that level of depth in year 12. So just keep that in mind. Now, this is going to look very strange to start out with. We've got two pictures. They're basically the same picture. What's happened is I've taken my length of wire, which is a straight length of wire, and I've curled it into some sort of loop. And what we're doing is we're kind of going to use this as an intermediate step towards more complex fields. basically you're asked, the current is going in one direction, going in there, coming out there. What is the direction of the magnetic field inside the loop, and what is the direction of the magnetic field outside the loop? We split our loop up into two areas, the inside and the outside. Inside the loop, the magnetic field is going to all be in the same one direction. Outside, it's going to be in the opposite direction. We're just asked to find which directions inside and which direction is outside. I'll be using some notation on a future slide about how we show three-dimensional magnetic fields, but I'm going to put that on hold for now. So if you imagine this wire looks like that, the current is going around this way, so I'm going to grip my thumb so that it is pointed along the direction of the current. I just need to pick one area of my loop that I'm going to stick my hand over. It doesn't matter if I pick it there or pick it there, I'm going to get the same results either way. So if I recognize there's some consistency with the magnetic field, and it doesn't matter where I put my hand, I'll get the same answer. I'll just put it here because it's more comfortable. Some of these hand positions, particularly with the right hand slap rule, which is going to be one that we look at in the future, sometimes there are multiple ways of positioning your hands so that you can get your answer, and if you position your hand in an uncomfortable way, then you might not want to hold it there for very long, and then you might not check that your answer is very good. And so sometimes you've just got to position your hand in a way that's comfortable, you know. So I stick my hand here, thumb is pointed around this direction, and I can see that inside my coil, if I go like try and get this perfect, inside my coil, my field lines are going to be pointing in this direction. My fingers are curling around like this. So inside, my magnetic field is going to be pointing into the loop. Outside, my magnetic field is going to be coming out of the loop. So inside, at any point, the magnetic field is going to be going in. Outside, at any point, the magnetic field is going to be coming out. It's basically just been, turned horizontal. This loop's just been turned to like that. I can see that inside the loop, the field lines are pointing up. Outside the loop, the field lines are all pointing down. If I stuck my loop like this and put my thumb like that, so my thumb's moving around in this direction, then inside my fingers are pointing up. Outside my fingers would be pointing down. So I can get my field line directions just using that kind of thinking. But here it's easy to show the field lines. And just in case you're wondering why there are all these red circles on here, it's basically just showing what the magnetic field would look like at any point that I might have chosen. I chose my point to be around here, which might be like that one or that one. And so that's my field lines produced at that spot. You can see that these circles inside, they're all pointing in the same direction, and correspondingly outside the loop, they'd all be pointing in the same direction. It's just another way of showing that doesn't matter which point you pick on your loop, you're going to get the field line results from your point being the same as the field lines at any other point in terms of whether they're pointing in or out inside the loop. So that's that. And here it's easy to draw the field lines because it's just up there and down there. I'm going to show you, like I said, the notation that we'd use for this one on, I think, the next slide. Yep, skipped the slide, spoiled it. So the example is draw the magnetic field around the following current carrying wire. Use the notation that X equals into the page and a cross equals into the page and a dot equals out of the page. Now that's the notation that we use when we talk about magnetic fields, because we're going to go into magnetic forces in a bit. And when we look at those, we've got a kind of three-dimensional system. And so if we've got our left and our right and our up and our down, that's very easy to show on a page. Showing something moving out of a page or moving into a page, that requires a sort of system for showing what's in and what's out. And using these crosses and dots, that's going to be our system for showing that if something's denoted by a cross, it's shown to be moving into the page. If something's shown by a dot, it's moving out of the page. Now, I didn't put this up on the PowerPoint, but the way that it often gets thought of is that, do I have some paper to draw on? I maybe should have. Yeah, whatever, I'll make do. You think of it as kind of being like an arrow. So you've got a cross on the end, then the arrow shaft, and then sort of like an arrowhead on the opposite end. So you imagine that if the arrow is coming towards you, you're seeing like a dot, which represents, it's not a perfect analogy, but it works, it does enough. If you see the arrow coming towards you, moving out of the page, then you're going to see a dot, you're going to see the kind of tip of the arrowhead. If it's moving away from you, the arrow, you're going to see the cross sort of like a feather type shape. So I'm just going to temporarily, I'm not going to try and do any sort of editing or restart. Do I have any spare paper? It'd be handy if I did. I'll grab this year, whatever thing, sack. Sorry, I really should stop the video and just restart it when I've got this drawn, or I should have put it up, but... Alright. See if I can get this. You got this system where if it's heading towards you, you see the dot. If it's heading away from you, if you're standing over here, then you're going to see the arrow. So if you're standing here, it's moving towards you. If you're standing there, it's moving away from you. That's the sort of mnemonic that just helps you remember where the cross is, which direction a cross signifies and which direction a dot signifies. But anyway, so if I wanted to figure out my magnetic field, like I said before, it's either inside the loop, going to be into or out of the page. It's really like, even if you just guessed, you got a 50% chance of getting this right, either it's in or out inside the loop with this out, and then it's going to be the opposite on the outside, but I want to have a better shot at this than 50%, so I'm going to actually get it right. I'm going to just pick out here is the area that I'm going to grip. I imagine myself gripping it, and this is kind of a visualization skill because you can't actually grip the thing. But you stick your thumb in this direction, the direction of the current, which is what the arrow signifies. And if I grip this outside the loop, my fingers are coming out of the page. So that coming out. Inside the loop, they are going into the page. So assuming that I didn't stuff this up, on my answers on next, I should see that out here, I've got out of the page, shown by the dots. Inside here, I should have into the page, shown by the crosses. Was I correct? Here I am, yep. So here, the magnetic field, if you imagine it, you've got magnetic field lines pointing into the page. Like I said, this is a three-dimensional system. So we're showing that the field lines for this particular slice would be going in, and the field lines here are coming out. Dots showing out, crosses going in. So it's important to remember those, or remember how to use the mnemonic to answer questions about these. Yeah. Now, the very last thing we do, and I got into the habit last year of making people do a little cutting and pasting activity as part of this, and you'd be doing that if you were at school. It's kind of unfortunate that you miss out. Maybe you do it when you come back. I like it, although students don't tend to, so yeah. But we take basically one loop of wire, and then we just keep looping it. We're taking a lot of loops of wire and putting them together, and that gets us one of these, which, put up close so you can see it. It's got lots of loops going around it, 100 by looks or something like that. Does it tell you? 660, that does not look like 660. Huh? Oh yeah, because there are layers to it. So this is what we call a solenoid, and it's something where if you run a current through it, just like with the loops shown before, it's going to produce a magnetic field. The convenience of a solenoid is that inside there's a uniform magnetic field. So if we look inside in this area, the magnetic field is going to be the same at all these points. Doesn't matter how far along it is. As you get out here, it's going to change in its strength. But inside is going to be essentially the same from point to point. The same way that when we did those two parallel plates, when we looked at electric fields, and we said that between those two plates, the electric field was the same from one point to another. This is the corresponding setup when we're talking about magnetic fields, where we've got a uniform magnetic field, and questions are often based around something's going on inside a uniform magnetic field, and so it's going on inside a solenoid. And then you can model the question where you've got something moving between a few different points, but you can still assume that the magnetic field remains constant. So that's the value in these kind of setups, the inside part where you've got your uniform field. Now, the field lines, they go all in one direction along here. Outside, they loop around from north, pointing out towards south. These field lines here that seem like they stop. Like I was saying about electric fields, I think it was, the field lines are actually going to continue around and meet up with the ones at the opposite end. It's just that we can't draw lines going off for kilometers down the road and taking up more heaps of space. So realistically, those are your field lines. They form closed loops like the ones you can see down the bottom. They come out, they go around, they go back in. So just keep in mind that that's the shape that we use. Now, a very common question, which is surprisingly difficult, is if we didn't have these field lines and we knew the direction of the current, draw the field line pattern around the solenoid. I haven't got a question like that, but I'll just walk through how you do that. So if you didn't know the magnetic field lines, then just like we were doing with that magnetic field around the current carrying wire, we should know the general shape that it's going to have. We knew with the current carrying wire that it formed concentric circles around the wire. We just needed to figure out the direction of the arrows on those circles. And it's a similar thing where if we didn't know the direction of the magnetic fields, if we didn't know that this was a north and that was a south, we only knew that the current was going in that way, then we could still draw this shape of the magnetic field. We just wouldn't know which direction the arrows were pointing. So step one, if you're asked to draw a magnetic field produced by a solenoid, is just to draw your general overall shape. And once you've got that in place, you can figure out, well, which end is north, which end is going to be south, because I haven't mentioned this yet, but just like any other magnetic system, the magnetic fields of solenoids have north poles, they have south poles. One end is the north, one end is the south. We could move this north to here and that south to there. Probably better not to do that just because it would then be on top of the field lines and wouldn't look as good, but just keep that in mind that these solenoids do have north and south poles, and you might get asked something like, well, figure out which end's the north pole, figure out which end's the south pole. Anyway, there's a few different ways you can do this. I find the most convenient way is that, and this requires a bit of thinking, we're going to use sort of like a reverse right-hand grip rule. And the way the reverse right-hand grip rule works is, before we were saying that our thumb was the direction of the current and our fingers showed the direction of the magnetic field. When we're dealing with solenoids, we can actually reverse that rule and say our fingers are going to curl around in the direction of the current. So you can see the current, it's coming down here, it's going up the back, down the front, up the back, down the front. So I'm going to, and this is going to be inconvenient, actually I can just reverse like this. I'm going to put my fingers like this, so they're going down the front and up the back. So my fingers are curling around in the same direction as the current. So up the back, down the front. So down the front, up the back. I can see that my thumb is pointing to my left in that situation. And that implies that inside the solenoid, the field lines should be pointing, well, because I've turned around, my thumb was pointing to the right. My field lines inside there should all be pointing to the right. So there should be arrows on here showing that it's going around here. And then you can see that outside it's just going in the opposite direction. So to the right here, to the left up there. I know that these arrows inside have to be pointing to the right by my reverse right-hand grip rule. If solenoid has an iron core inserted inside it, it becomes stronger. This setup is what's known as an electromagnet. We'll be doing stuff on that in our next area of study. We look at power generation and transmission, and we do stuff on transformers. Hopefully you'll be back by then, but if not, I can set up a little demo and show you how that would work. And just, I haven't mentioned this yet, it's important to keep in mind, it's called the right-hand grip rule. If you do it with your left hand, you're going to get the exact opposite result, because if I put my one hand up like this, my fingers curling around there. I stick my right hand up like that, my fingers curling in the opposite direction. You need to use your right hand to do the right hand grip rule, otherwise your answer will come out wrong. Just keep that in mind, that don't just think of it as the grip rule, think of it as the right hand grip rule. Remember your difference between left and right. If you get stuck, some people do. I want to say there's no shame in it, but I think it is sort of shameful. So yeah, just remember, if you do that, you've got an L, it's your left hand, boom, you know not to use that hand, use the right one instead. I think that's pretty much it for this lesson. There is a chapter in your book on magnetic fields. I think it is 2.3. You should be working on that as part of today's lesson and then doing some of the Ed Rollo questions.